I just wasn't sure that the program with China is going on. Apparently it does. All right. So hi everybody. My name is Stas Bורוב. Let me turn it on. Not a lot of students here today. Hopefully it's just because it's 9 a.m. It's hard for everybody to get here with all the rain and traffic. Anyhow, the class is usually very big, around 100 students. What happened? Fixed it. Great. There are 3 hours of lectures, 1 hour today, 2 hours tomorrow, between 12 and 2. Both of them are in this class lecture room. I will give you my details a little bit later, but usually you can always find me in my office. It's room 314, room number pi on the 3rd floor. My email and other contact details are in the class website. And I will describe you the technical details about, okay, so what are the constituents of the grade, etc., by the end of this lecture. All right, so before we go to specifically what we are going to study, I want just to explain what is statistical mechanics is about. Right? And in statistical mechanics, there is a word, statistical. Some statistics has to be involved. But before we go to the statistics problem, I want to describe to you a simple problem that was investigated originally by this guy, Henri Poincaré. He's a mathematician, a French mathematician. Physicists usually, well, we don't really know him until we start to learn about chaos and chaos theories. But actually he published almost together with Einstein the theory of special relativity. He was late by 2 weeks. Okay? So Einstein got all the credit, but Poincaré was almost there already. Now this problem of three bodies, you all solve two-body problems, right? In mechanics, you solve it when you do deal with waves. We always solve two bodies, right? So the next step after we solve two-body problem is to solve a three-body problem, right? The interactions between the bodies, when we're talking about two-body problems, it's as long as the interaction is on the same line that connects the two bodies, it's always solvable. Why it's always solvable? You can always make a transformation of coordinates into the center of mass, and voila, you have two separate systems, the system that describes the center of mass motion, and the coordinate that describes the distance between the two masses. And we can completely solve those problems. Whenever we are dealing with three-body problem, this trick does not work anymore. Moreover, Poincaré solved that this is a chaotic problem, meaning that when you take initial conditions and you shift them slightly, a little bit, okay? So what do you expect? You expect that after a while, because you made a small change, tiny change for the initial conditions, also after a while, the system behaves almost exactly the same. But this is not what happens in chaotic systems. Extremely minor changes for the initial conditions cause extremely large and different behaviors after a while. Right? So we cannot simply solve three-body problem, and it always creates some crazy pictures. Great. So three-body is not solvable. Now, if you look around us, you look on almost every object that you have, it does not have one mass or two masses or even not three masses. It has huge number of masses, right? So if you take this meter by meter of air, we have around 10 to the power 23 Avogadro number of particles inside. They are all interacting with each other. It's not just three bodies, but 10 to the 23rd power particles that are interacting together. if we don't know how to solve three-body problem, how can we solve a general, any physical problem that involves huge number of particles, right? So this is a quadrangle, in a sense. You have many, many particles. They are somehow interacting. We know that if you take small portion of it, the interactions cause chaotic motion. We have huge number of particles, so we kind of lost, right? From the standpoint of usual mechanical mechanics or quantum mechanics, all the problems around us are not solvable. Now, you can think about any problem. Yes, actually, yes. Think about motion of those particles. Think about even the current in a very simple in a very simple setting like this, right? So you have a bulb, you have a plus minus battery, and so you have a current going round and around. Yeah, I can solve it, right? V equals R multiplied by I. But if you think about it, what happens inside? So those tiny electrons interact with huge number of atoms that are sitting inside these wires. Those wires are not exactly periodic structures. They're a lot of disorder. So the particle performing a random motion, jumping from one, one atom to another, to third, to fourth. How can we solve anything over here, right? So huge number of interactions. And the purpose of statistical physics, statistical mechanics, is to answer those questions. How, and we know, yes, we know that indeed we can model the current inside, inside the bulb. We can describe how many photons approximately are going to be emitted from this bulb, etc. So we do know how to deal with the world around us, but we don't, well, at least you and I still don't understand how it's possible. Right? Huge number of interactions, unsolvable problems, and, well, somehow it works. And it works due to our knowledge of thermodynamics and statistical physics. And basically, the answer to this, we have to forget deterministic thinking. We have to forget anything that relies, well, I know exactly what's the situation right now, so I can solve a bunch of problems, or a bunch of formulas, bunch of equations, huge number. They're extremely, extremely difficult, but I can solve them. And after a while, I get exactly one answer, and everything is predictable. Okay? So the nature around us, it's not predictable. It's not predictable due to two reasons. Reason number one, we already learned about quantum mechanics. The underlying structure of all the laws of physics is probabilistic. Quantum mechanics does not deal with exact positions of particles. It deals with wave functions. What is a wave function? The absolute value of a wave function is probability. The other reason why the world is probabilistic is because of what I told you in the previous slide. We have too many interactions, we have too many particles. So those complexity is basically something that you cannot deal with. You cannot simply say, it's a complex thing. I can shove it into a computer, it can be a quantum computer. I can shove my problem into a quantum computer and it will solve it for me. It won't work. Even with the capacity of a quantum computer, any quantum computer that you can imagine. Just too many interactions. The complex system is simply too complex. So by the words of Ayn Rand, you can ignore reality, but you can ignore consequences of ignoring reality. So we cannot simply say, well, forget about it. Let's deal with this. No, you simply can't. Why? Because otherwise you'll be stuck with trying to solve too long equations. So when you forget about deterministic problems, you're left with probability. And whoever took my probability class, it's a fantastic subject, mathematical subject, but the thinking is very, very different from almost anything else. It's quite odd sometimes, this probabilistic thinking. So in statistical physics, we start to forget about positions, we start to forget about velocities, we start to forget about all of those things. We deal with averages, variances. And in this class, almost all of the behaviors are going to somehow well, till we reach something that's called phase transition, but almost everything will depend on this law of large numbers and the central limit theorem. Forget about positions, forget about velocities, think about averages, variances, probabilities, and Gaussian central limit theorem. Eventually, you can say, well, you're forgetting about everything. You left with average, you left with some probability function, etc., etc. But even we forgot about all the constituents and we forgot about that there are huge number of particles, we still can predict, explain, and understand fascinating behaviors in nature. So, like for example, this superconductivity and levitation. It's based on mathematical description of the law of large numbers. Right? So you cannot explain it specifically by saying, okay, what happens to each particle in this current? But if you try to explain it statistically, somehow you obtain a different behavior and superconductivity pops out. Phase transitions. Okay? So what we have over here is a boiling water. You see there is water molecules and there are bubbles of air. So those are two different phases of matter. And the transition between one phase to another, if you try to see what happens to each molecule, it's simply extremely complicated and you cannot reach any understanding. But the moment that you forget about this intrinsic description and you try to explain everything in terms of averages and probabilities, you can explain, you can predict the critical temperature when the boiling of water will start. You can explain the size of those bubbles of the water, etc., etc., etc. Yes, you don't know what happens to each and every particle in the system, but you know and explain the general and large behavior. Same thing happens for active motion and swarming. So those are flocks of birds that are behaving together as if there are some waves of matter, water. And this is just to explain. So at some point, statistical physics is very general. At some point, you can forget that you're dealing with birds, or you're dealing with atoms, or you're dealing with people, or you're dealing with worms. The statistical nature of the behavior, at some point, simply does not care. Jamming. So probably you experienced this this morning due to the weather. You can describe jamming of cars, or you can describe jamming of particles, atoms, birds, and the physics is going to be exactly the same. The generality of statistical mechanics is I forget about the complexity in some sense. I forget about the behavior of each and single particle, and I don't really care who it is. It can be a driver, it can be a bird, or it can be a Cooper pair, or just two electrons somehow bounded together. Their statistical behavior, that's what's important, and this is what I can describe. Therefore, the laws are going to be general. Yes, we will mostly deal with simple systems, even not water, simpler than that. But the applicability of the laws that we will describe is actually very, very, very broad. Couple of few words about statistical mechanics. So the part of statistical mechanics that we're going to describe is statistical mechanics of equilibrium. So equilibrium is something that is, well, I define it later today, but equilibrium is something that it's not changing as a function of time, generally speaking. Okay, so everything that is changing as a function of time, even this glass of tea, is not an equilibrium. Okay? So if you think about it, you look on the tea, there is a lot of vapor. Well, now it's not too hot, but there is vapor that's coming out. So water molecules are escaping somehow from the tea itself. This brings the tea to lower temperature. Okay, so it's going towards some equilibrium state, but it's still not there. If you think about ourselves, we're definitely not in equilibrium. Right? We constantly consuming food, energy, glucose, and we constantly get rid of it, otherwise we will explode. So we, or all the living systems around us, most of the living systems around us, are out of equilibrium. Part of the systems, the simpler ones, are in equilibrium. So if you take a usual something, okay, so for example, this table, and you look on it as a function of time, you see that the table and its temperature probably is not changing. So the table is in some sort of an equilibrium. Okay. This is nice. But sometimes if you look on something a little bit more complicated, like this glass over here, okay, so this is plastic, so I don't know. But if you look on glasses, glasses are rigid objects, okay? They do not seem to us as if they are changing as a function of time, but they actually are. On a micro scale, there are flows, very, 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 very slow flows, but glasses are systems that are out of equilibrium. We won't deal with out of equilibrium systems in this class. This is reserved for some other classes. So we will deal with simple problems where there are no dynamics, there are no currents, and everything is stable and dead. And you will see that even for such simplifications, physics is extremely, extremely hard, sometimes. So this is hardness and different point of view that you have to address when you're dealing with those systems. This is what brought this David Goldstein. It's a nice book about statistical mechanics. So he starts these books as follows. Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it's our turn to study statistical mechanics. So it's kind of a joke, but if you we already talked about probabilities and etc., etc. So this is the distribution of the exam grade in this class. It's not done on purpose, right? So it's not that here is an evil Stas that's trying to fail all the students. It happens on its own. Okay? So the moment that the exam questions are not exactly, and sometimes even if they are exactly the same as were in the previous exams, people are going, or huge portion of people are going to fail. So if you look, the average or median is somewhere over here, and the 60 is because of some small factors. The class is tough. The point of view is different from what you used to, usually. So I advise you to come to the lectures, or at least see them during the semester, solve all your homework, not just copy it, solve it actually in groups, by yourself. Do not think that if you can postpone everything till the last week and then in a very fast binge cover all the material. It won't soak in, you will fail. Okay? So this is usually what happens to all of those people. Hopefully you won't be there by the end of this class. Now, during the semester, homework, it's obligatory. It's 11% of the final grade. Quiz, 22%. We already set the date. I will publish it. I think it's on the 8th week of the semester. It's somewhere in December. I will publish the exact date. And the final exam is 67% of the grade. Okay. That's it. Any questions before I start in the last 20 minutes that we have to cover some actual material? Yes?
Is the quiz normal or is it again?
Okay, so great question. And before that, don't hesitate to ask questions during the class. If you're afraid that your English is not perfect, it's fine. My English is bad. If you're afraid that you are incapable of expressing yourself, ask the question in Hebrew. I will translate it. But do not hesitate to ask questions. It's very important. Regarding the question, is the quiz obligatory or it's a Magen grade? Well, usually it was obligatory. So everybody had to take it. Last year, because of the war, I made it a Magen. I haven't decided yet. I will see. Hey, the moment that I will publish the date, I will also publish if it's Magen or not. Any other questions? Yes.
טוב, יש משהו חשוב, זה שאנחנו מנסים עכשיו לדחות את התאריך של המבחן, וצריך חתימות של כולם, אז כאילו אם תוכל להודיע למי שרוצה שיסתכל, שלחנו מייל.
Okay, so the question announcement is that there is a general request, yes, to postpone the date of the exam. So I'm not sure that everybody wants the right this date or not. So the student, what's your name?
Betzalel.
Betzalel is asking for everybody to come to Betzalel and sign the petition to postpone the date of the exam. Question, why the date is so bad? The exam or the quiz?
לא, פינאל אקזאם.
Okay, so why it's so bad?
נופל ממש בתחילת תקופת המבחנים על מבחן שיש למלא אנשים במקביל.
Okay, so I don't really care when the exam is going to. Nobody really asked me, right? It's not that I'm setting the date of the exam. I only set the date of the quiz, but I don't really care. So there is a group of people interested to postponing the date of the exam. Come to Betzalel and talk to Betzalel. That's it? Yes.
Why should we remember good from Pennsylvania?
Good? You should remember Bina. She's very good. So what we are going to use from thermodynamics, and I'm going to cover it a little bit fast, are the laws of thermodynamics. But you will see that the laws of thermodynamics, that how I presented, they are somewhat different from what you learn in thermodynamics class, basically because I'm going to treat them variationally. So, in a sense, if you liked analytical mechanics, right? So in analytical mechanics, there is Lagrangian, and there is action, and you say the laws of physics are coming from minimization of some function that's called action. Okay? So I'm going to describe to you the laws of thermodynamics by minimization of something. Okay, so similar principle. You haven't seen this in thermodynamics, so it's going to be new, but the outcome is the same. I'm going to cover thermodynamical laws, and actually afterwards we're going to step away from whatever you learned over there, and we will treat phase transitions, and we will treat statistical mechanics, etc., etc., etc. So not a lot, but thermodynamics is essential. This is why I also cover it in the first two lectures or so. Yes?
Is there a book that you recommend?
Yes. So, but it should appear on Moodle if the Moodle is already updated. But the books that I use are the book of Chandler, Introduction to Modern Statistical Mechanics. There is a book of Landau, Statistical Physics. And there is a third book that is actually, but I forgot the author name. So, but it's on Moodle. There are 3 books. I do not go exactly by the book or one single book, so there are always jumps and something that I bring from my own perspective. But there are books. Yes.
In your presentation, you showed the Drude model.
Mm-hmm.
That is an example of a statistical system that has a current in it, right?
Yes.
So we're not going to cover that?
No. No. But its Drude model explains currents,
exactly.
right? And it's very complex. So from the Drude model and a lot of interactions and a lot of rebounds of the electrons, you still obtain a very simple formulas, right? But we're not going to cover it. No.
Which courses cover
The Drude model, so you usually will see it in class on condensed matter or non-equilibrium statistical physics. That's it? All right. Great. So we will start with laws of thermodynamics. There are 3 laws. We'll see what we'll cover today. So we are starting with the first law of thermodynamics. Now, before we explicitly state what is the first law of thermodynamics, because it deals with energy, so before going into what exactly this first law of thermodynamics, we will state the simple thing that, well, the problem of thermodynamics is to describe in very few, using very few variables, systems that have huge number of constituents. Okay, so few variables describe huge number of constituents. Constituents can be particles, atoms, people, whatever, right? So if you want to keep a number in your head, it's the Avogadro number, 10 to the power 23. We cannot have 10 to the power 23 different variables, right? And then the thermodynamics tells us, well, you should keep only few of them. Probably the most essential one is energy. So we want to use energy in order to describe stuff in thermodynamics or any statistical problem. Okay. Now, what we say that is the internal energy of the system. And we assume something about this internal energy of the system. We assume that the energy is extensive quantity. This is going to be our assumption through all this class. Okay. What does extensive means? Do you know? You heard this name, extensive?
Yeah.
Yes. Yes, what it is?
It grows with the system.
Exactly. So it depends on the size of the system. Not just depends on the size of the system, it's basically proportional to the size of the system. It's growing linearly with the size of the system. So basically what I'm saying is that if I have, this is my box is my system, and it's composed of two subsystems, and if the internal energy of system A, it's EA, and the internal energy of system B is EB, the energy, total energy, is going to be E equals to EA plus EB. Okay? Now, it's not only for those two systems, but any general system that is separated to many subsystems, right? So we have E1, E2, E3, E4, E5. The total energy, E is E1 plus E2 plus E3, E4 plus E5. But do not be mistaken. It is an assumption, right? It is an assumption. When I'm saying that the energy is extensive, I assume something. What have I assumed? Or I neglected something. In physics, we always neglect something. We cannot solve everything. We always neglecting something. What I have neglected when I said that the total energy is EA plus EB. Yes. Interaction. Or the energy of the separation. Okay. So there is always a contact between different subsystems. Okay, so there is some interaction between system A and system B. The moment that I said that this my energy is extensive, I'm neglecting all the interactions or whatever sits on the boundary between the two subsystems. Is it good? Is it bad? Why should I neglect it? So physically, in most systems, it's going to be fine. Why it's going to be fine? Because if you think about it, so I have a lot of particles. right? I have a lot of particles. Those particles are interacting with a lot of things. Okay? So this I have particles that are black. Here I have particles that are blue. But the main thing is there is usually a range of interaction of each particle. So if we look on each particle, there is a, generally speaking, specific radius around this particle, and this particle interacts only with other particles that are sitting inside this radius, right? There is some specific range of interaction for each and given particle. Now, so there are some interactions between the black particles and the blue particles. Like for example over here. Those two particles interact with each other. So the energy depends, always depends on the interactions between whatever sits in system A and whatever sits in system B. But what saves us is this huge number. The number of particles inside system A is extremely large. The number of particles that sits in system B is also extremely large. And the number of particles that are interacting between system A and system B, because of the finite interaction length, so something that sits over here, is extremely small when you compare it to the number of particles inside system B or inside system A. Therefore, I can always neglect it. Okay? So you can say, oh, but this is always true. It's not an assumption. You neglect something which is small. But you always have to be careful in physics. Right? You always neglect something, but you have to think, well, I neglected it, so I should keep it in the back of my mind that for some systems, that can be wrong. What systems do you think this assumption of extensivity is not going to hold?
Very small systems.
Sorry?
Very small systems.
Very small systems. It's not going to work. We have different kind of statistical mechanics over there.
Or when the interactions are...
Interactions are extremely large. So for example, gravitational systems. Right? Think about it. What is a gravitation? Gravitation are forces that are decaying as 1 over r squared. Decay of gravitational force. The moment that you have this long decay, so it's not that you're only interacting with something over here, you're also interacting with something, maybe slightly, something that's over there. Okay? The moment that you have such parallel decays of the forces, extensivity is out of the window. Okay? Sometimes, the only thing that you have in your system is the boundary. Sometimes you want to focus on the boundary. So for example, if you look on a glass of water, and the only thing that you care is the water layer between the air and the water, it have very different properties than the bulk of the water or the air itself. And this system is, again, not extensive. Why? Because you're just focusing on this part. You can say, well, Stas, but it's not just gravitational forces decay as a parallel. What other forces do you know that decay as a parallel? Electromagnetic forces. So I cannot use statistical mechanics on electromagnetic systems, right? That's what I'm saying to you. Wrong. Why? Because sorry?
No, continue. If they are large enough.
No. There is screening. Right? So if you think about it, if I indeed have two atoms or two electrons, the force between the electrons goes as 1 over the distance squared. But if you have a lot of atoms inside, there's always screening. And the force, it's not decays as a parallel, it decays as exponential. You can say, well, exponential decay, parallel decay, who cares? The problems of mathematicians. But it's very important. You have a finite range of interaction for forces that decay as exponentially, and you don't have a finite range of interactions that forces that are decaying as parallels. So for electromagnetic systems, it will work as long as we have screening inside the system. Basically, big number of particles. So in all those systems, what saves us and this is very basic thing in statistical physics, and it's very useful, you will see this, is that we always somehow saved by huge number of particles. I started this class by saying, oh, there's huge number of particles, it's awful, we cannot solve anything. But actually you can solve a lot of things, because this guy allows you to assume extensivity. Extensivity lets you kick out of the system interactions. No interactions, well, kind of nice. You will see that we can solve, again, most of the problems somehow are going to be mapped onto two systems that physicists can solve. What are the two systems that physicists can solve? One, harmonic oscillator. There is a simple one, free particle. Right? We can truly solve two systems, and everything else it's some kind of a mapping of those two systems. We will see that most of the cases, because of extensivity, we can map either to system without interactions or to harmonic oscillator. All right, great. So, what is the first law of thermodynamics? I told you about that the energy is extensive, right? But the first law of thermodynamics, when you assume that the energy is extensive, says the obvious thing. The energy is conserved. This is the big deal about the first law. The only thing that you have to know, well, the energy inside the system is a conserved quantity. So, if you look on dE, what is dE? Change of energy. Okay. It equals to what? So, if you change the energy, somehow, something else operated inside the system. So, thermodynamics, remind you, going back to the end of the 18th century, 19th century, a lot of heat, engines, so they were concerned with heat. Okay, so you can cool down your system or heat it. This cooling down or heating of the system amounts to some change of the internal energy of the system. So it is amount of heat that got into the system plus dW. Well, usually we have the change of energy equals to the work. Here, because of this heat, we also have this heat inside, but the change of energy it equals, well, we can modify the energy by heating it or cooling it or applying work on the system. So this is work performed on the system. Great. Now, let's just write down what this thinking behind this dq and this dw. So, what is dq? Again, I remind you, it's thermodynamics, so the thinking is of 19th century. 19th century, there was a big revolution, and it's not about the French Revolution, it's about the revolution that caused by engines. Right, so if you have water, okay, you put a fire under this water, the fire heats the water up, you put a wheel over here, the wheel starts to rotate. If you build the wheel properly, the moment that it's rotating, let's call it with some frequency omega, the moment it's rotating, you can use it to produce work. Okay? Now from this time of this very simple engine to our times, This is always what we do to produce any kind of work. So if you think about it, this electricity, where it comes from? From the power, from the electric, right? How do they produce electricity? What they do? They burn something, right? They burn something. There is because of the burning, there is a magnet that goes up and down inside a huge coil, and because of the magnetic forces, there is a current, and this current eventually what lights up those bulbs inside our homes, right? So it's always burning of something. There is a sun, right? Sun energy, but it's also burning of something that is far, far away, but it's still burning of something. So this is heat. And it's very hard to control it. So usually what they say, it's not a true differential, okay, because it's not work. So this is heat. Heat energy. Now there is also the work that was performed on the system. Okay. So we will write it down in a vector form, which is f dot dx. What is f and what is dx? F are generalized forces, which are intensive quantities. Remember, extensive, like energy, it's something that depends on the size of the system, usually goes linearly with the size of the system. Intensive variables are independent of the size of the system. What is dx? dx are generalized coordinates of the system. So this is intensive. Generalized coordinates of the system length, the system volume, number of particles inside the system. So this is extensive variables. Usually they depend linearly on the size of the system. Okay? Let's see a few examples. So for example, we can say the work that we performed is due to the pressure minus P external multiplied by dV. What is this? External pressure. This is volume change. We can say dW is tension multiplied by the length of the system. We can have other generalized forces, like the chemical potential that we will discover later. In general, when I say that dW is f dot dx, I can say this is f1 multiplied by dx1. There is some generalized force and associated coordinate that connected to this force. Conjugate variables, as we will see later. There is another force, another generalized coordinate, and etc., etc., etc. We will see more examples of it, and specifically, we will see how to treat this ugly guy, because yes, I can explain what is force, what is work. Yeah, force multiplied by extension, right? But what is this? And how to treat the heat? It's a more complicated question. So for now, we state the first law of thermodynamics, which is simply conservation of energy, that is described by this equation. Alright, so this is the end of it, and we will continue tomorrow. Yes?
It shouldn't be minus the double?
It depends, right? So it depends of the work that you done on the system or the system done on the outside. So this is the work that I performed on the system. Okay? This is why I have the minus over here. Great. Alright, see you all tomorrow. כן.
השיעור של יום שיעור כאילו היה יותר משמעותי מבחינת האורך?
יש שעה ושעתיים. היום שעה, יום שלישי שעתיים.
אז שלישי זה כאילו השיעור היותר...
יש גם שיעור קצר הוא משמעותי. אבל כן, יותר ארוך, הוא שעה וחצי. פה זה 45 דקות ושעה וחצי יום. כן. לא חייבים, אני מבלבל בין הזה לבין הדיקי, לא צריך.